So we're going to do a lot of graphing this year, and today we kind of set the foundation for the method or methods in which we're going to take and graph a lot of different things. Let's start by talking about parent functions and transformations. So parent functions are like a stripped down car that you buy at a dealership. It's like no air conditioning, AM, FM radio, so on and so forth. And what we're going to do is we're going to beef that up a little bit as we go through the lesson and show you how to do stuff. But we're going to look at the parent functions first. So an absolute value function, if we were to graph that, you should have probably had some of this in Algebra 1, but it has a basic pattern in an XY chart of, if I put input values of the numbers 2 through -2, I get a 2, 1, 0, 1, 2 out. And then I graph that, and you'll notice it creates kind of a V function starting at the origin. So something like this, okay? And every absolute value is going to have that look to it. And the base of the pattern is going to be this right here. Now, if I'm to graph a quadratic, that's just a parabola, all right? And that general pattern, again, I'm going to often use these same numbers as long as they are in the domain of the function. Get out a 4 and a 1 and a 0 and a 1 and a 4. So in graphing this, this is more curvilinear, if you will, or parabolic in shape, like so. And every graph of a quadratic will look something like that. We move to a square root function. Now, I'm not going to pick those same numbers because we can't pick negative numbers and put them into a square root. We only pick numbers, well, I'm going to pick numbers that are perfect squares. You can actually pick pretty much any whole number, but not all whole numbers like 3 are perfect squares. So if I look at these 3 numbers, which are all perfect squares, they have all integer values out. So they graph nice and easy. Get a 0, a 1, 4 over 2 up, 9 over 3 up, and this is a function that goes kind of one way out forever. Cube root, or cube, sorry. Cube, again, this is defined for all real numbers, so I'm going to go back to that same pattern of x and y being -2, -1, 0, 1, and 2. We get an 8 here, a 1 here, a 0 here, -1 here, and a -8 here. So you'll see that this looks significantly different than the other ones that we've graphed. 0, 0, 0, -1, -1, -2, -8, like so. This comes up and goes on forever that way and on forever that way. And then finally, we're going to look at a cube root. And again, just like perfect squares, we want to pick perfect cubes. So I'm going to go with -8, -1, 0, 1, and 8. Because 6 is not a perfect cube. Nothing multiplied by itself gets you that. So these all have integer value answers. It's kind of just the opposite of what we just did. All right, so now I start graphing. Go out to 8 and up 2. And go back, and this looks similar to that. So these aren't the only functions we're going to graph, but there are base parent functions for this point in time, and you need to know what those look like at this point. Now, so it turns out that every function, the ones we've done and every other one we're going to do, kind of conform to this basic equation, all right? And what we have graphed up to this point is y equals some f of x. Well, there are things we can do. Like I said, the parent function was a stripped down version, which was this, y equals f of x. What we're going to do is we're going to play around with these functions, all right, and actually do a whole lot of things with them based on these things that are added. All right, and the first thing we're going to do is we're going to mess around with a k value. So you'll notice I have three graphs here, x squared plus 4, and x squared plus 2, and they're all color-coded. So if we look at each of these graphs, you'll notice, I guess, they kind of appear to be in a different shape right now. I mean, some appear to be wider because these other guys fit into it, but they actually aren't. They're actually the same graph of the parent function, which is x squared, except you'll notice when I add 4, the whole graph moves up 4. When I subtract 2, the whole graph moves down 2. And the reason why I know they're the same is the pattern, or this, base parent function, is the same in every problem. If I go over 1, I go up 1, over 2, up 4. Likewise here, over 1, up 1. I'll do it in a different color. And this goes over 2 and up 4. And then on the last one, if I go over 1 and up 1, then I go over 2 and up 4 from point to point. So it's really the same graph. It's just been what we call translated by the k value. So in essence, k translates all points up or down, depending on the value of k. Next, we're going to mess around with our h value. So the h value is inside here. And in this case, our h value, while it looks to be -3, h is actually equaling 3 here because it's the value that follows a subtraction sign, whereas h in this case is -4. So you'll notice, again, color-coded for an absolute value graph. And in this case, if I have an h value of 3, we notice that this black graph, which is the parent function, gets moved to the right 3. When I make h -4, then we notice this parent function slides over 4 this way. And it's much easier to see in this case that these are really the same graphs, just moved. Because I go over 1, up 1, over 2, up 2, over 1, up 1, over 2, up 2, over 1, up 1, over 2, up 2. All right, so it is the same graph. It's just been translated again, but in this case, the h affects the translation left to right. So h translates all points left and right. Okay, positive h to the right, negative h to the left. All right, so let's hit the next one. So now we're going to look strictly at the a value. And I know this is an a value because it's what I call outside of the function. The function, f of x, or the parent, in this case, is root x. And in each case here, we have multiplied that root x by something. Now notice our parent function pattern is right here, which we saw earlier in our earlier slides. And we notice that each of these points is starting at the same spot. It's still starting at 0, 0. So this has remained the same. Now, if we look at this graph of 3 root x, here's our parent function over 1, up 1. This goes over 1, up 3. All right. And then this guy goes over 4, but up a total of 6. All right. Now, normally we go over 4 and up 2, and this is now 6. This was over 1, up 1, and now it's 3. And you look at when we go over 9, we're all the way up at 9. So you'll notice what's happened is all these y values have basically been multiplied by 3. All right, which is a pretty significant thing. All right, and then if we take and move to this half x, you'll notice in this case that when I go over 1, that I go up a half. And when I go over 4, I'm now going up 1. And when I go over 9, I'm now going up 1.5. All right. So you can see that each of these y values has been multiplied by 1/2. All right. So in essence, we know that the graph itself has not moved. It's still starting at 0, 0. So there's no translation because the h and k don't exist. But my y values have been affected by this a value. And that a value, what I call it, is I call it a y multiplier. And what it does really is it really affects the shape. It's not the same graph as the parent function. It looks different, okay? They also call this a stretch factor. And they can also call it, when it's pushed down, they call it a compression. All right. So in this case, the a multiplies to the y value. All right. Next, let's look at our last term that we haven't spoken about, which is the b term. Now, b is inside f of x because it's inside these parentheses. And you'll notice its position is in the denominator. So if you'll notice in this problem here, it looks like we're dividing by 3, but actually the b value isn't a third, it's actually 3. If you see something like 2x, but it's inside the function, that 2 is affecting the b value, but it's not in the denominator, it's in the numerator. So a way to say a multiplication of 2, but to do it by dividing, is dividing by 1/2. So in this case, b equals 1/2. So now we have to figure out, okay, what effect do these numbers 3 and 1/2 have on this function? Well, you'll notice something similar about these graphs. They all have their dots on the same y value, all right? But it's the x values that change. So let's take a look at those x values. This black is, and these are all going by half intervals now. So this is 1 here, and this is 3 here, all right? So we go over 1 and up 1, that's no change, and we go back 1 and up 1, that's no change. So the black graph is the parent function. Let's take a look at what happens. How do we get up to 1 in the blue graph? We go over 3 and over -3. So you'll notice it's still up 1, but we've gone over 3 and we've gone over -3. And then notice, how do we get up to 4? Normally in the parent function, we go over 2 and up 4. There it is. But in the blue graph, we go all the way over to 6 and all the way over to -6. And you'll notice that if I were to take that x value and multiply by 3, we get 6 and -6. Likewise, let's do the same for the half. So you'll notice now, if we take and move over, how do we get up to 1 again? We're going over right to here, which is actually 1/2 and -1/2. Well, if I were to take and multiply 1 by 1/2, I get 1/2. -1 by 1/2, I get -1/2. All right. And if I were to multiply my original value of 1 by 1/2, that's exactly what happened. Now let's go to our second values. So in my second value, I would normally be going over 2 to get to 4. But now in order to get to 4, I'm going over 1, and I'm going over -1. So you'll notice that if I multiply 2 by a half, I get 1, -2 by a half, I get -1. So in reality, what this b has done is it's affected the x values. So I call b an x multiplier. All right, and again, when b is greater than 1, it's going to take and expand or press this out. All right, so we still have the stretch factor and the compression factor when that b value is less than 1, except now it's stretching and compressing the x values. So let's sum all this up in one slide. So if all these graphs can be expressed as some y equals a f of x minus h over b plus k, the h moves this graph horizontally, either left or right. The k moves this graph vertically, up and down. The a stretches, all right? It's also called a dilation, I didn't mention that. Or you can say it compresses, all right? So when a is actually greater than 1, it's going to narrow the graph but stretch vertically. When a is less than 1, it's going to make the graph wider, okay, or compress vertically. We haven't talked about this, but if a was a negative value, it would reflect those points over the x-axis. B, we said, was the horizontal stretch factor. And when b is greater than 0, it opens the graph wider or stretches it wider relative to x. When b is less than 0, it narrows the graph, all right? And when that narrows the graph, it compresses it horizontally. And if b were negative, it would actually reflect, it would take x's going from positive to negative, so it reflects over the y-axis. So now we're going to look at a more complicated function and use these new techniques to graph it in a much simpler way than just plugging points in and getting points out. Okay, we're no longer going to plug and chug. We're going to use these new principles. So the first thing I'm going to do is I'm going to give values for a, b, h, and k based on this graph. And I notice there's no multiplication outside the function. I'm going to put a 1 for a. There's no division inside the function. I'm going to put a 1 for b. H is what follows a negative sign on the inside of the function. So that's 3 in this case. And k is what's added or subtracted to the outside. So in this case, that's a -2. Now, what this has done is it's translated every point 3 to the right and 2 down. So I know that this parent function is x squared, which has values that we normally plug in of -2 to +2. And this is my general pattern that the graph will look like because there has been no stretching of the graph or compressing, because a and b have not changed. There's no x multiplier, no y multiplier. So the graph is going to look exactly like this graph would be. It's just going to move. So what I'm going to do is I'm going to move the vertex. 0, 0 is going to go to the right and down 2. So what I usually do is I put a little like crosshair right where that new origin is going to be. And I put my new origin right there. And now I know this is the same exact graph as x squared. It's just been moved. So if I go over 1 and up 1, I get to a point. If I go back 1 and up 1, I get to a point. If I go over 2 and up 4, I get to another point. And if I go back 2 and up 4, again, I get to that other point. There's my graph. And notice I never plugged into this function. Although what I'm going to do, and I tell my kids all the time, do not walk away from the problem until you've checked one point. And that point should not be the vertex point. All right. So I see this point right here, just counting. This is a point 1, 2. Now, the point 1, 2 should check in this formula here. So 2 is my y value. I'm going to plug in 1 and hope that my output is 2. Notice, this is 1 minus 3, which is negative 2 squared. Negative 2 squared is 4 minus 2. What do you know? 2. It checks. So this graph is an accurate graph for this function, and I never had to plug into it except one time to check. That's going to be the goal. We're no longer plugging and chugging. We're using the concept of translations and stretch factors to graph. So let's do another one. Same situation as last time, except we have a cubed function. We're going to take and identify a and b. Both in this case, since there's no multiplications or division inside the function, is going to be 1. My parent function is x cubed. So I know this is going to look like 2, 1, 0, negative 1, negative 2, 8, 1, 0, negative 1, negative 8. H is what comes after a subtraction sign, so I would have to have a subtraction of negative 2 to get an addition of 2, so this is a negative 2, which means it pushes all the points to the left 2, and this is a negative 4 for k, which means that's going to go down. Again, I'm going to translate my origin back 2 and down 4. Put a little crosshair there to indicate that's my new origin. And because I have no compressions or no stretches, because there's no multiplying factors of a and b, I can graph this pattern and be certain that that is an accurate graph. So I move over 1 and up 1. I move over 2 and up 8, and back 1, down 1, and back 2 and down 8, which puts me somewhere down here. And there's my graph. So again, I'm going to pick a point before I'm all said and done and check it. So I'm going to say this point is going to be 0, 4. That's an easy point. And when I plug 0, 4 into this, it better check. So 4 better equal 0 plus 2 cubed minus 4. This is 4 equals 2 cubed is 8 minus 4. 8 minus 4 is 4, so check. That's an accurate graph. All right, now today all we covered really was what each individual transformation did, and then we combined it with translations. We haven't changed the shape of our graphs in a multiple transformation type of graphing problem. We're going to do that tomorrow. Okay, so stay tuned.